So page 81, here we go. We have 4 types of things we call particles. Okay, particles are little tiny bits of matter, and you could have an atom, and you can see they're just usually represented by like a little ball or something like that. Okay, and so a single atom on its own, not stuck to anything else, is just an atom. If you have atoms that are stuck together by covalent bonds, whoops, forgot the S on the beginning of stuck. This is page 81. And we'll talk more about what covalent bonds are in just a bit. If you have atoms and they are stuck together by covalent bonds, and you just have a little one, or even like a big one, but it does have some finite size that it is limited to, because DNA can be really long, but it has a finite size. Like, it's not like it could just keep going and going and going forever. Then if you do have that, then you have what we call a molecule. Molecules are always held together by covalent bonds. Another type of particle is the ion, and you'll always recognize an ion because they have these charges at the top. So ions are charged particles. And then finally, this is the one you've probably never heard of because it's not used outside of chemistry specifically, is called a formula unit. Okay, and a formula unit is a single unit of an ionic compound. Single unit of an ionic compound. And you will see later in this document that they don't actually just exist like that. Like you would, this is table salt, NaCl, sodium chloride. You'll never see like a single sodium ion and a single chloride ion just by themselves. You'll just never see that, okay? But it's a useful mental construct, so we give it a name, okay? Now, let's take a look at these in more detail. Atoms. You'll notice that unlike the ions, the atoms do not have a charge. They are neutral. They are neither positive nor negative, okay? They do contain positive and negative charges, but overall they are neutral. An atom is the smallest component of an element. And our elements can either be metals or, as you can see on the shaded portion of this diagram here, they can be the non-metals. Okay, so the non-metals are over here, and the metals are here. And oh, who else is shaded? Hydrogen. Hydrogen is actually a non-metal, even though it's over on that side of the periodic table. Okay? So atoms could be nonmetals, atoms could be metals. They're just whatever particular type of element. And while we're here, we might as well take note that over this group on the far right, these guys over here are the noble gases. Okay, we'll review the rest of them in a bit, but those are the noble gases. Now, what do metals tend to do when they're just hanging about in nature? Well, at room temperature, what they do is they tend to clump together in very, very regular arrangements. So you can see here, we've got a very regular crystal-like structure. They're very organized, okay? So you have single atoms, but then they get together in large congregations to form these crystals, okay, crystal solids. There is one exception, and you should know this, is that mercury, Hg, is a liquid. And if you recall, hopefully last year you learned this. If you didn't, I'll teach it to you now. A little subscript at the bottom with a little L means liquid, okay? So maybe this one is sodium, and so we have sodium with a little subscript at the bottom, and we say solid. And that's made of sodium atoms. Mercury is a liquid. You can see that although the particles are still really close together, they're sort of all jumbledy, okay, rather than being very organized in a solid. And so that is our liquid. Non-metals, some of them are gas at room temperature. Chlorine's a gas, oxygen's a gas, hydrogen's a gas, helium's a gas, and all of those are non-metals. So we've got a gas here, and a gas here, and a gas. Fluorine's a gas, chlorine. Bromine is kind of funny. Bromine is a liquid. Most of our noble, oh, guess what? Our noble gases are gases. I don't know what it happens when we get down to I don't even know what that stands for. OG. OG. Nitrogen is a gas, but not all, oh, and hydrogen, not all nonmetals are gases. Bromine is a liquid, okay? And all the rest of them are solids at room temperature. So the only two liquids that we have at room temperature, mercury, don't have COVID. It's my smoothie from lunch has fiber. Anyway, and it's in my throat a little bit. Br, bromine, are liquids at room temperature. All the other metals are solids. Non-metals, you can see we've got the ones I colored in yellow are gases, and then the other ones are solids. Carbon is a solid. Okay, you may have seen it, like charcoal is a solid. You might have seen sulfur piles out in Port Moody, those yellow piles of stuff, that is sulfur. And it is a solid. But if we're talking about atoms here and we're looking at the particle nature of matter, only the noble gases exist as atoms rather than as molecules. And remember, an atom versus a molecule, atoms are singular, molecules contain more than one atom. So only the noble gases look like this. Okay, so if we go on to our next page, and tell me if I'm moving too quickly at any point, you can be like, slow down, okay? Molecules are also neutral. In other words, they have no electrical charge. They are neither positive nor negative. The only particles that aren't subatomic particles, because electrons and protons are subatomic particles and they have charges, but the only particles that have a charge are the ions. So molecules are neutral, no positive charge, no negative charge. Molecules are only made of non-metals. So look over here, these are our non-metals. You're probably familiar with that staircase on the periodic table, okay? And don't forget hydrogen, because it's off on its own, way on the far left of the table. So remember hydrogen. Molecules are always made of two or more atoms, okay? If it was a single atom, it would just be called an atom, all right? They are bonded covalently, which if you recall from last year, means that they share their electrons rather than one atom giving its electrons to the other one. They actually share their electrons. And again, we will look at that in more detail later, but what it would look like, the most simple one we could look at hydrogen. Hydrogen has a single electron in its shell. And if you had another hydrogen, okay, with a single electron in its shell, they will actually get together and they will share their 2 electrons. Okay, and remember, electrons are negative. We'll get into this more in the next unit. I'm just giving you a little preview here. Okay, remember in the nucleus, there's the protons. Okay, in hydrogen, there's only 1 proton. But what happens is you have these positively charged protons in the nuclei, and in between them, you have these shared electrons, which are negative. And what do positive and negative do to each other? They do cancel, but they also do something else. They attract. Positive and negative attract. Okay, so the positive is pulling on the negative, and it's pulling on this negative. This nucleus is pulling on the electrons. This one's pulling on the electrons. And that pull is what we call a covalent bond. Okay, that is a covalent bond. And that only happens in nonmetals. So if you've got a molecule, molecules by definition are held together by covalent bonds. And covalent bonds are only between nonmetals, because metals don't really like their outermost electron very much. They're happy enough to give it away, so they tend to do things like bond ionically, where instead of sharing, they just give their electron away. Okay, so if you have a molecule, you know it's going to be made of nonmetals, and you know it's going to be bonded covalently. And molecules are funny. It confuses people sometimes because they think, oh, I've got 2 or more atoms, it has to be a compound. But molecules can actually be elements, right? You can have a molecule of an element, and all that means is that the particles are all the same, with the atoms are all the same within the molecule. I have an I and I have an I. These are identical. Since they are identical, it was actually I for iodine, but I decided to make it I for identical. Identical atoms mean it is a molecule of an element. We have a single element. You can see we have P4. It's got a funny kind of a structure. Okay, it's like this little pyramid kind of deal here. And these little sticks that we draw in between the atoms, those are the shared pairs of electrons. That's representing, you can imagine that in here we have an electron and we have another electron, okay, and those 2 phosphoruses are sharing those 2 electrons. Okay, so those sticks in between the atoms represent the covalent bonds. We have sulfur. They're all sulfur, but they're bonded together covalently. And finally, down at the bottom, we have oxygen. Oops. Oxygen and oxygen. And you'll notice that this one actually has 2 covalent bonds. Between it. There's 2 sticks in between the 2 oxygen atoms. That means we have what we call a double bond. Okay, so there would be 2 electrons here, and there would be 2 electrons here. These models, the way we've shown them, are called ball and stick models, because you've got the oxygen, which is the ball, and then you've got the sticks in between, which are the bonds. Okay, so molecules can be plain old elements, only one type of atom. But what if you have more than one type of atom? Like over here on the right, we have an oxygen atom. Yes, here's our oxygen atom, and it's bonded to two hydrogen atoms. We have different types of atoms, two or more types of atoms. And in that case, we have molecules, but when we have two different types of atoms, we call them compounds. Compounds are compounds of more than one element. So this is a compound of oxygen and hydrogen. This is a compound of carbon and hydrogen. Okay, this is methane actually, CH4, methane. Ooh, exciting erasing things happening. Methane, okay. And you'll notice the, just while we're here, we might as well take note. These little numbers down at the bottom, you can see we have H2Os. What that means is that we have two hydrogen atoms attached to. There's nothing down at the oxygen, so that means we just have one oxygen atom. CH4, there's nothing down at the bottom of the C. That means we just have one carbon, and you can see one carbon there. And we have four hydrogens. 1, 2, 3, 4. And then, oh my gosh, what is this thing? I think, if I'm not mistaken, this is caffeine. I think I got caffeine for you. It might be nicotine, but I think it's caffeine. And it is a compound of carbon, hydrogen, oxygen, and nitrogen. Okay, and it's super complicated. You can see, I mean, if you were to go through and count, you would find 10 hydrogens, 8 carbons, 2 oxygens, and 2 nitrogens. All right. There is another way of representing molecules, and those are called space-filling molecules. Space-filling molecules more accurately represent what the molecules really look like. Like if you could actually get in and look at them in real. When does class end? Class does not end at 2:25. That's on regular days. On Wednesdays, it ends at 2:45. I know. But you're welcome to like just leave me and read it on your own. If you're tired of me, okay? So, space-filling models. Space-filling models more accurately represent what a molecule is really like. What a molecule actually looks like. Actually looks like. However, they both have their advantages because it's kind of nice to see, oh, look, oxygen has a double bond, which you can see up here. It shares 2 pairs of electrons. You cannot see that in the space-filling model. So we use different models in different circumstances. Particle type number 4, ions. They have an electrical charge. They have either lost or gained electrons. Do you guys know what the prefix mono means? Mono means 1. Yeah. So if you have a monatomic ion, monatomic, 1 atom, you only have 1 atom. Or do you remember hearing about polyatomic ions, maybe last year, grade 9 as well? Poly means many. So a polyatomic ion is going to have many atoms, well, or at least 2. It'll have 2 or more atoms, and they are going to be bonded together covalently. Okay. And here are a couple of new words for you, or possible new words. I don't know if you learned them last year. Cations, not cations, cations. It looks like cations, but it's pronounced cation. They have a positive charge, and they are always formed from metal atoms. Okay, so cats, you can remember that because cats have paws. So cations are positive. Look at that cute little cat. I went and found that little clip art with him showing his little paw there, his little paw prints, okay? And I really want you to appreciate this because I also went and found, because anions are negative, okay? And onions kind of sounds like anion, yeah? And I found like a crying onion for you, because onions can make you cry, and that is a negative thing, yeah? So anions are negative. Or you can just remember a negative ion spells anion. Either way, whatever you like. But appreciate the little clip art because I thought it was really cute, okay? Okay, so we could have a monatomic metal cation, because remember, cations are always metals, as long as it's monatomic, and anions are always non-metals. And in the next unit, we'll look at why, but for now, you're just gonna believe me, okay? And you can represent them. If you're writing the symbol, you just write Na+, okay? If you are writing like a little model form of it, you can either put the plus charge on the inside of the little, you know, circle, or you can put it on the outside of the circle. It doesn't matter, okay? Either way, you can show that you have an ion by having that charge there. Here's some pictures of polyatomic ions. In the 2 units from now, you'll get really familiar with these. There's actually only 2 polyatomic cations. Only 2. And I've drawn them both for you here. One of them is ammonium, NH4+. Okay, and you can see its ball and stick model here. It's a nitrogen, which is a nonmetal, bonded to a hydrogen, which is a nonmetal. And remember, nonmetals and nonmetals bond with covalent bonds. They share a pair of electrons. You can also see the space filling model. Now I'm going to mess with you because I've got mercury, which is a metal, and it's actually bonded covalently to the other mercury. And metals aren't supposed to bond covalently, but mercury is just a weird little thing. Mercury is the only liquid at room temperature, right? Yeah? It's bonding covalently to itself, right? Like, that's just weird. And it's the only metal that forms a polyatomic cation. Hg2+. What's up with that? Well, if you have mercury 1, that tells you that the charge of mercury is +1. What that means is each individual mercury has a charge of +1. But together, +1 and +1 equals +2. Okay? And I'll remind you of all of this when we get closer to the end of it. And remember, these are positive ions because cats have paws. Here's a couple of polyatomic anions. Remember, onions make you cry, so that's a negative thing. So we have hydroxide here. There's our covalent bond in between our 2 nonmetals. But this whole thing has actually gained an electron, because when things are negative, they have gained electrons, which means that ammonium had to, the whole thing between out of the nitrogen and the 4 hydrogens, it had to have lost an electron. Okay? You can either show the charge outside of a set of brackets, or you can show it without the brackets when you're showing the models. Either way works. Those are your ions. And we're almost done, I promise. Formula units. This is the weird one. A formula unit is a single neutral unit of an ionic compound. It's made of ions. It is made of charged particles, but because you have both positive and negative, they cancel each other out and they come out neutral. In nature, you cannot have cations and anions on their own. You won't walk around and find a big pile of sodium ions. What would be wrong with this picture? What would nature do if you piled a whole bunch of sodium atoms close to each other? What does a positive charge do to a positive charge? They do not attract, they repel. So these would all like repel, right? And they would fly apart. You would get a big explosion actually. And that is why cations and anions do not exist on their own. They have to be with each other because they stabilize one another, okay? Wherever you have a cation, you will always have an anion. And it will make the overall charge neutral. An ionic crystal lattice, you have alternating positive and negative charges. So you can see this three-dimensional structure, right? It goes up and down, it goes side to side, it goes front to back, right? And it alternates positive, negative, positive, negative, positive, negative. Now you could take a single slice of this and it would look like that. And often we will draw it like that. You have gotten that slice, you can actually take a single one of them. Isn't school done? No, school is done because we start late on Wednesdays, we finish at 2:45. Yeah? I know, we're never gonna finish the course otherwise though. I know it sucks, I wanna be done too, I wanna go home. Okay, but we'll be done in 5 minutes, promise. Pinky swear, pinky swear. Okay. So look at this. If you take a single one of those, that is called a formula unit. Okay? And I think at this point, is there anything else we need to, oh, look, we're at the questions. So the only thing you need to know is sometimes we don't show you the positive and negative charges. Sometimes we'll just show them alternating. If you see that alternating arrangement, you know that you have a crystal, an ionic crystal lattice. And did I promise we'd be done? Yeah, we're done. We're done. You're excused. Everybody's excused. Do you need to go back where the homework was? There we go. So if you've forgotten, there it is. Thank you guys for attending so patiently and wonderfully. Okay, and I will see you tomorrow.